Hello everybody, in this lecture we will be solving 1993 IMO problem number 1. Here is a view of this problem. We are given a polynomial of degree n and we would like to show that this polynomial given in this format cannot be expressed as the product of two non-constant polynomials with integer coefficients. So I guess the best way to attempt this problem would be to assume to the contrary that it is possible to in fact express this polynomial as the product of two polynomials and then try to find a contradiction from that. So let's begin then. So let's assume to the contrary that f of x in fact can be written as the product of a of x times b of x, where both a and b, the polynomials a and b, have degree greater than or equal to 1, and they also have the following form. Let a of x can be written as a sub k x to the power k, so it's a polynomial of degree k, a sub 1x plus a sub 0. And similarly, let b of x can be written as b sub m x to the m, and so on, b sub 1 x plus b sub 0. And here obviously we need to have k and m, the degree of these two polynomials, between 0 and n, and thus their sum is equal to n, because the leading coefficients, so the leading terms when multiplied, they should give you the leading term of f of x. Okay, but then realizing that the leading coefficient of f of x is 1, this would imply after multiplication, if I should multiply a of x and b of x, the constant terms would be a0, b0. So let's start with the constant term actually. a0, b0 would be the constant term, and we can see that the constant term here in the polynomial f of x is 3. And for the coefficient, the leading coefficient, so we would get a sub k, b sub m, and that one is equal to 1. So starting, for instance, from the second one here, so this would imply simply that a sub k and b sub m, they are both either 1, they are either both 1 or they are both negative 1. For the first one, for this first condition, we can, without loss of generality, assume that one of them, let's say a sub 0 is equal to plus minus 1, and b sub 0 be plus and minus 3. So if a sub 0 is 1, b sub 0 is 3. If a sub 0 is minus 1, b sub 0 is minus 3. Next, I will make the following observation. Especially what I have in mind is when I inspect each of these terms, the coefficients in this polynomial, I realize that all the coefficients are divisible by 3 except the first and the second term here, the leading term, the leading coefficient, and then the next coefficient. So that gets me with the following extremal argument. So let L be the least index such that 3 divides not b sub L. So since we already know that b sub 0 is equal to plus or minus 3, so it is divisible by 3, but we also know that b sub m, that one is plus or minus 1, so not divisible by 3. From there, we have that L will be greater than 1. Sorry, I should say 0, right? So because b sub 0 is already plus minus 3, so it's divisible by 3, so L cannot be 0, but it can be 1 actually. So L is definitely greater than 0, and look, b sub m is 1, so not divisible, so it can be as high as m actually, so somewhere in that range. Okay, now I would like to consider, so consider at this step the coefficient of x to the L, consider coefficient of x to the power L in the polynomial f of x, right? In f of x. which is simply, remember, is equal to a of x times b of x. So let's consider the coefficient of x to the power L in that product. Well, when you multiply out the terms, so the coefficient of x to the L basically would be the following sum, product sum I should say, a sub L minus 1 b sub 1 plus all the way to a sub 1 b sub L minus 1 plus a sub 0 b sub L. So that would be the coefficient of x to the power L in the expansion of f of x. Knowing that b sub L, L is the least index such that b sub L is not divisible by 3, suggests that b sub 0, b sub 1, all the way to b sub L minus 1, they are all divisible by 3, implying that this whole term is divisible by 3, versus this one, because b sub 0, this is a 0, a sub 0 is plus or minus 1, it is not divisible by 3, b sub L is not divisible by 3, as a result this last term is not divisible by 3. And it's because of the observation that we made early on. So if we rewrite, if you remember the expression f of x, remember it was this expression plus 5x to the power n minus 1 plus 3. Now we just observe that all the coefficients are divisible by 3, and there's a lot of zero coefficients, obviously you can interpret it that way, except the leading coefficient and the next coefficient, which are not divisible by 3. Because all the other coefficients are divisible by 3, L cannot be L cannot be n up to n minus 2, right? So L can be so L is definitely going to be greater than or equal to n minus 1 as a result, right? So that does that make sense? Because L cannot be anything n minus 2 or lower, because all these coefficients are divisible by 0, and it's impossible by this analysis that we just did, because if it was divisible, because we know that the coefficient of x to the L is not supposed to be divisible by 3. Okay, so therefore L has to be greater or equal to n minus 1. But early on, if you remember, we had this other condition. So therefore, bringing that back, so we have these two conditions. And by the way, m is less than n. We mentioned it way earlier this way. So therefore, combining these two bounds for L imply that there's actually only one possibility, and this is the possibility where L is actually equal to m, which is equal to n minus 1. But if that's the case, then recall that k plus L was equal to n, and as a result, because so this would imply that k plus, and remember that L is just n minus 1, so this is equal to n, implying that k has to be equal to 1. But k is the degree of the polynomial a of x, right? So therefore a of x, this implies that therefore a of x is simply equal to, because now we have that k is equal to 1, it is just a sub 1 x plus a sub 0, that's it. So a sub 1 x plus a sub 0. But then early on we already made notes about the leading coefficient and the constant term for a of x. If you remember, for a of x, the constant term was 1 or negative 1, and the leading coefficient was also 1 or negative 1. So as a result, our polynomial is in fact a of x is equal to plus minus, sorry for that, come on, I don't need this, so it's plus minus x and then plus or minus 1, so the order doesn't matter in this case, so it's either way, suggesting that the roots of a of x is either 1, the root is either 1 or negative 1. So here order is, it can be anything, it can be either this or it can be plus minus x minus plus 1, right? So therefore you can have both roots. So but if remember, any root of a of x will also be a root of f of x because f of x is equal to a of x times b of x. So as a result, let's test if that's possible. If we test f of 1, we just realize that plugging into its form here, we would get 1 to the n plus 5 times 1 to the n minus 1 plus 3, and that will give us a 5. And finally, f of negative 1 would simply be equal to that won't give us a 5, that would give us a 1, 6, 9. So what was I thinking there? Okay, so that one would give us a 9, and then for the other one, we will get a minus 1 to the power n plus 5 times minus 1 to the n minus 1 plus 3. First one I can write it as minus 1 times minus 1 to the n minus 1 plus 5 times minus 1 to the n minus 1 plus 3. So therefore this is a common, we can put them together. So therefore we would get 4 times minus 1 to the n minus 1 plus 3. But regardless, okay, so that regardless, we observe very well that so the first term will be plus or minus 4 and the second term is 3. Therefore from here, if it's plus 4 we will get a 7, or if it's minus 4 we will get a minus 1, but both of them are not equal to 0 regardless. So 9 is not equal to 0 and these guys are not equal to 0, suggesting that this gives us pretty much the contradiction that we were looking for, right? So this is the contradiction. So as a result, we can conclude neatly that f of x, our assumption was wrong, and f of x cannot be expressed as the product of two non-constant polynomials with integer coefficients. So that solves our problem. Just as a side note, I would like to encourage you to consider solving this problem in the complex domain actually. That would also very neatly give you the result that you want. If I have time in the future, I will come back to this problem and probably provide you with a solution in the complex domain. So thank you for watching and hope to see you in our next lecture.